Voilà. Okay. Good morning, everybody. Thanks for being here. So we go on with the third lecture on rudiments of graph path theory. So first of all, I would like to make a correction with respect to what I said last time. In fact, I decided, and I already did it in the notes that you probably retrieved from the web, that for the second component of a graph path, I would put the index 2 alpha and not alpha. This is just a notation, but I checked in the books, and that's what they do. And it's also, imagine that you draw poorly this symbol, then the 2 alpha reminds you that you are dealing with the second component. So it has some advantages. However, before I found some advantages not to put the alpha. I switched to the standard convention. So last time we defined graph path. Today we are going to finish this exercise with an explicit example of convergence in the graph path topology, and then we'll go on to start to define some slightly unusual integrals that we don't hear much about in the classrooms when we are young, but which are nevertheless useful and rather nice. So first, before I start, any questions about the previous lectures? If not, then let's move on. So let me remind you what we did. We started with a very simple family of paths. This is the parameter, and this is the time parameter, let's say, and it depends on some external parameter epsilon, and we wanted to study the limit when epsilon goes to basically 0 plus. And what we showed was that first point-wise, and then we did some more computations, at least for the first component, to see that it's better than just a simple convergence. Then the pair Z epsilon and its second component. Oh, I will try to improve on that. So there was a limit, and this limit was non-trivial in that the first component, so the path itself went nicely to 0 in the Euler topology uniformly, whatever, for Euler topology for any alpha less than 1/2, and then it could be. We also showed that there was simple convergence, so the most naive convergence for the integrals towards something, a second component which remains non-trivial in the limit. And if you look in the notes, but it's easy, you can do it for yourself. There is also the proof that in fact this convergence is not just point-wise, but that you can improve this convergence. And now we would like to elaborate on this a little bit to try to understand what we should do with this equation if we understand that this is somehow a graph differential equation. So this is just to give an explicit example which will hopefully illustrate that it's useful to have this concept of graph path, because it allows to take certain limits in an almost naive way, and limits are better behaved with graph paths than if you just look at the first component. So the point is that, in fact, it turns out this equation is well. So first of all we just start with we are going to define. First of all, this for the moment has no precise meaning. So let's try to see what we can do if we look at the smooth version, so which we take as an equivalent to these are smooth paths. This is a smooth path, so we define it. So what we interpret this. When I say equivalent, it's an interpretation. So d epsilon over dt is w bar epsilon d z epsilon over dt. So the advantage of this little example is that it's not totally trivial, but nevertheless manageable. And in fact, it's easy to see by substitution. You take a second derivative, you use the definition. This is explicit, of course, because we have this formula here. So this is, okay, so this is just explicit. And then I leave you to check the following, that in fact, okay, I'm sorry, I want to put an initial condition, I'm sorry, so W0 is equal to 1. So we start at the origin we start at point 1 in the complex plane, times 0, and we look what goes on. So we keep the same normalization, W epsilon 0 equals 1. And then, so we have the similar equation for the complex conjugate. So we take a second derivative and then do the algebra, and I let you check. It's really elementary, that what you end up with is epsilon d2 w epsilon s second derivative ds squared. I don't know why I switched to s as a parameter in the notes, but let me just follow the notes. This is easily seen to be I dw epsilon over ds plus w epsilon. Okay, so this is, so now you see, well, this one it doesn't look very nice, but this one looks already much nicer. This is a linear second order equation, so that's something we should be able to deal with. And we just noticed that it's singular when epsilon goes to 0. Okay, so now, trust me, if you define omega plus and minus to be 1 plus or minus square root of 1 minus 4 epsilon divided by 2 epsilon. By the way, if anybody finds, well, I know there are famous combinatorialists in the audience, if anybody finds a natural reason why the generating function of Catalan numbers arises in this problem, I'm interested. I don't. Well, that's the way it goes, if I made no mistake. Then what you get is an explicit formula that it splits in two pieces, which I call epsilon plus s plus w epsilon minus s, and w epsilon plus minus s is just, if I made no mistake, one divide. You can check. So I will need some other. Wait, it's not the problem. Plus square root of 1 minus epsilon. Ooh. That's not what I wanted, so I'm sorry. Plus minus s is going to be, sorry, 1 divided by 1 plus epsilon omega plus minus to the I omega plus minus s. And in doing so, I'm making, I want all these guys to be, is that correct? Yeah, okay, yes. I take epsilon less than 1/4. If epsilon is larger, then there are real parts in the, here everything is purely imaginary. Yeah. Omega is also rotating in a certain way. And of course, as you can guess, if I take epsilon equal to 0, I see that in fact, there is one of the solution omega minus is nice and it's just rotating in a trivial way. And in fact, the singular one comes is the one with omega plus. Okay. Again, doing the computation the right way, what you get, it's, you see, okay, so if you, for instance, if you think about it, so omega epsilon minus, let's say, is nice, and omega epsilon plus s, you can rewrite in a very simple way as 1 divided by square root, what I call epsilon plus square root 1 minus epsilon plus z epsilon plus, and I just have defined epsilon plus b1 over omega. So I'm just rewriting things. This one is nice, and this one is in fact essentially the original path we started with in these guys. There is a small normalization, there is a small change. You see that when epsilon goes to 0, this behaves exactly like for plus, this behaves like 1 over epsilon. So this is really, this is really this in these guys. Okay. So everything we understood for the original path, we can reproduce the computations very easily for the complete path. And what we get is that, in fact, doing a little bit of algebra, what you find is that the limit when epsilon goes down to 0 of w, and what is the, that's the canonical notation for blackboard w, epsilon, you get that there is this is a non-trivial thing, so a w and wt is equal to e to the it. This is just, as I said, w minus is nice. You can really take limits naively. You see when epsilon goes to 0 for w minus, this is just 1. So this is this is where the piece in w. This comes from w minus. W plus is going to do just as z is going to 0. So the limit is just given by w minus. And then for the second component, you get again something which is non-trivial, which is what you would expect from this guy here. So e to the it minus e to the is squared divided by 2, where you recognize, so maybe, well, maybe I missed some I somewhere, I don't know. Okay, so that's the naive part. That's what comes from w naively by doing the double integral. And then there is again an anomaly, which is t minus s 0 minus I 0, which is the one that comes from this path here from z. So this here you find that there is a naive plus, and this is the anomalous part. Okay. So now the little point I want to make is the following: is now what happens. Yes.
So here, what you have explained so far is it gives the first component, the limit of the blackboard. With the computation, so you get
W plus is essentially z, and it goes to 0 when epsilon goes to 0. This looks like epsilon, in fact, for small epsilon. This is of order epsilon. And W minus is nice. It would be the solution of this guy essentially. And if I made no mistake, this is the solution of this equation is that. Okay, there is one that contributes to the singular solution. It's W plus, and the one that contributes to the non-singular solution is W minus.
And the prefactor in front of W epsilon plus is something tending to. I cannot.
It's a computation.
Sorry, I cannot think.
Oh, I'm sorry. It's. You see, this goes to 0, this goes to 1, so this goes to 1. It's just algebra. I don't want to waste too much time on it, but I'm afraid.
No, but then, okay, sure. It's not about algebra, but about interpretation. So is it enough to conclude that for the blackboard W, you also have convergence of the blackboard W?
Well, it's easy to do the computation, and that's what I did. Maybe there is some kind of more abstract argument. I did it very explicitly. You just compute. So you compute the double integral with finite epsilon, and you let epsilon go to 0.
But you have to do it. I mean, you don't have at this stage, you don't have an argument to say, this is what I mean. So you have a computation which you did not write and which gives you
yes.
the result on the.
There
is a jump from what you write here and what you write on the top of the board.
So I think it wouldn't be too difficult to say that because this one splits into a nice part and an ugly part, we also have we have this result. I guess so it should be able to do it at a more abstract level, but that's not what I did. I did it in the most stupid way. And I agree with you that having a theorem somehow to tell us that this is what is going to happen would be useful, and I guess such a theorem exists. And I have to admit that I don't know it. But I believe the theorem exists. What happens when epsilon goes to 0 for the differential equation? And then, okay, there are two news for the differential equation. The first one is that the equation has a naive limit, and the bad one is that in the limit z is identically equal to 0. So in the limit we get, and I put quotes, dw is equal to w bar times 0. And w epsilon goes to 0. W epsilon does not satisfy the equation. And what I want to show you now, well, make you think that I'm going to prove something, and I want to really show that, like an exhibit, is that if you're more careful and interpret this equation as a half differential equation, then you're in a better shape. And that's the way it goes. Well, it's totally elementary. So it's just to make sure. So let's forget about W, Z, etc., and look at an equation more abstractly. Imagine that you have dpt is equal to pt bar dqt. So you imagine you have two paths, complex, and you have this equation. Of course, this is the same equation, but I don't want to keep the same names, but because I want to think of Q as a generic object at the moment. And of course, if you do a small amount of algebra, you will see that it's essentially reproducing what we did in the, this is the one-dimensional complex case. You just reproduce the computation we did for the one-dimensional real case. So you interpret this as in the most naive way by saying that Pt is equal to Ps plus integral from S to T Pu bar dQu, and you do one step more, and what you get is that this is going to be Ps plus Ps plus PS.
The one above too.
I'm sorry?
The one PT just above is PS.
Yes, thank you. And then, if you are naive, so what you get is, as usual, I mean, I'm just repeating essentially things I already told you. S2U P V D Q bar V dQu. Okay. And if you want to deal with this a la Euler, you are going to say, okay, let's make now the approximation that PV is essentially equal to PS. And so what we get is an approximate equation, PS plus P bar S Qt minus Qs plus PS times the double integral. I mean, that's something you are used to now. So let's do it. dq bar v dqu, and now you substitute. So you substitute pt. You take it to be w epsilon. Qt. You take it to be z epsilon, and you get an approximate equation now. W epsilon t is equal, so I'm just reproducing W epsilon s plus W bar epsilon s Z epsilon t minus Z. I'm sorry. Oops. It's Z without the Z epsilon t minus Z S plus W epsilon S, and now the double integral that you know. It's okay. So it's T S to U D Z epsilon V D Z epsilon U. Okay, so no real surprise with this. And of course, now you can take the limit very gently, and what you get is W. I let epsilon go down to 0 naively somehow, and I get this equation that this is going to be Ws plus W bar S. This one is going to 0, so this is times 0 plus W epsilon, I'm sorry, Ws, and this one here is going to converge to what I announced there, and if I made no mistake, this is just going to be E T minus S, okay? And you see that, well, without surprise, this has disappeared, but there remains one term of order T minus S. So this essentially says that indeed now Wt is equal to the IT. Okay, because I get because. See, this is enough if I it's negligible. So this is. So this means that indeed we had this convergence of the path z towards something which was a rough path. And then, in fact, for the associated controlled differential equation, we have convergence towards a rough differential equation that we should write as W equals W bar and D, probably something like this. The meaning of this equation being that indeed we have to, the solution of this is some function of S and T, which is such that the difference, this here is equal to this plus negligible. So, which means we have all the terms of 2 order T minus S. There is probably, I guess I already said it, but let's say it once more. In fact, I don't know if it's just because we are used to it, but when we see a differential equation like dx over dt is equal to f of x, and we saying that x is a solution is nothing but to say that xt is equal to xs plus f of, let's say, xs t minus s plus a little o of t minus s. So this is equivalent to say that saying that this is solved is equivalent to saying this. And but how can I say, this is something we see we understand immediately as something, and we never think of it in those terms. However, for this half differential equation, as far as I understand, there is no other way to interpret it than going back to this definition that in fact you have all the terms of order T minus S. I don't have a global understanding of this equation just as I have such an equation here. Which is, yes.
But I mean, this way of thinking is analogous to the second order differential equation. Just did the same thing.
Oh, you can. Okay, so yeah. So
now, then the question is, can I write always for this structure some second order differential equation that has a similar behavior?
I don't think so. But well, this is a good question that I agree with you that in fact somehow the fact that you have to go to second order is remnant of the fact that there was a second order differential equation. You're totally right. I had not thought about it. So, but I don't think you can do this in general. You see, this is really a very, very special equation. So if you look at something more complicated, I guess there will be theorems that will guarantee that indeed the right way to take the epsilon go to zero limit is to look at the half differential equation, but I don't think you can just view it as a limit of the second order differential equation. Okay, so yeah.
So here you write, okay, this symbolic equation, and you say the meaning you have to think is second order.
Yes.
But here again, it's just for the first component. So do you have also translation for the equation for the second component for the
Well, that's also a good question. We shall see that in certain circumstances there is well, I guess the answer to your question is yes. So I wouldn't be able to give you an argument from scratch, but indeed, when you, it's to be expected that indeed when you solve this equation, W will also come as with a second component that makes it a rough path in a canonical way. That's correct. Yes. I did not show it at all, but I will, if I have time, I will show you circumstances when, well, maybe I can say this let's. Okay. I'm not sure I will be able to cover this during the lecture, so let me just take 5 minutes to, I hope, answer in some way. So imagine that you have imagine that x is a rough path, and because I write only two components, it means a two-component rough path with an appropriate exponent. And imagine that you are in such a circumstance that there is some other path, and which is such that yt minus ys can be written as something that is called y prime s. This is just a notation, it's just another path. Xt minus xs plus, let's say, order t minus s to the 2 alpha, and I guess that our order alpha, I take it as usual in 1/3, 1/2. Doesn't matter that much, but so we imagine that there is some object here, and you ask that this one is also alpha Hölder. This is okay. So there is this is a bit misleading, but there is another use of the word control. We say that in that case, the path y is controlled by x. You see, this is exactly meaning that if you look at short distance behavior of y, it's going to be no worse than the one at x. You see, there is some path. So if this is fluctuating widely, this is only possible if this one is fluctuating widely. Okay, so this is called the control. Anyway, okay. So this is, yes.
Is it assumed implicitly that y prime s does not depend on t?
Yes, it's just, you see, it's just a Taylor, it's just a kind of Taylor expansion.
Yes, indeed, but this is what you have written here is completely abstract. I mean, actually,
Yes.
y prime s is not a derivative of y; it's something different.
Well,
It's a Taylor expansion in usual life.
It's kind of a Taylor expansion, but you see the dependence. If you see, the point is the following: as ys is, this one is supposed to be alpha Hölder. You see that if I replace it here by yt, this can be put there. So there is no real origin in this case. Does this answer your question somehow?
More or less, yes.
Okay. So then so I will, maybe I will not have, then there is a canonical this is the right way. I'm not sure. Forgive me for this. This is really not beautiful, I guess. Is this the way you write down? Okay, anyway. So there is a canonical y constructed by using x and y. So this is not exactly this circumstance. This is a little bit different, but this is one of the instances where you, a priori, you only have y to start with, and nevertheless, there is in an automatic way a canonical second component that comes with it via an explicit construction. So I guess this would work as well for differential equations. I hope I will have some time to discuss this, but I'm not totally sure. So I prefer, as this is, well, important somehow, so that may be a good opportunity to state it. Okay, so the moral is that of this is that if you think in terms of rough path, rough differential equations and all that, then in fact there are many instances when taking a limit will go of differential equation, controlled differential equations with smooth sources will go through to give you something in terms of rough differential equations. And you can really the limit goes through, which is of course, it doesn't if you interpret this naively by forgetting about this stuff. So there are theorems that I will not quote, not even quote, that indeed tell you that in fact there is some kind of that kind of stability holds. I mean that of, well, I don't know if it's stability or commutativity of limits or whatever, that you can take the limit and then solve the equation, or take the solve the equation and then take the limit, and this gives you the same. Okay, so now we can switch to something which looks rather different, but which is in fact related. And I'm afraid this was supposed to be the funny part of today's lecture. So I hope you had fun up to now, because this is over. So we turn to the next chapter, which is, I give it a generic name. And this is something I'm not very happy with the title, because this is the standard name of what I'm going to tell you about. But in French, the laine de couture doesn't look too good. Anyway, so this is chapter, I don't know which, I forget about the name of the chapter. This is it. So let's motivate a little bit what we are going to do. We are going, in fact, to do something that may look rather abstract, but which is, in fact, extremely useful. So imagine you need to define some analog of the Riemann integral. So whenever you do so, in fact, what you are going to do is going to be the following. You are going to approximate, in some sense, the integral by some kind of finite quantity. You see, this is symbolically. You imagine you want to describe something that you write as this. This is just purely a symbol. So this is this. Okay, so then has Riemann sums, limit of Riemann sums. Then, well, what you will do is start by saying that, okay, that when S and T are close enough, then this integral delta gamma u is going to be of order of some object that you call gamma st, which is explicit. And use to approximate integral AB delta gamma u is going to be the first approximation, the sum. Again, this is symbolic. Gamma S Tm plus 1. So there are subdivision. This is what you are going to do. And just to illustrate it more precisely, when you do things a la Riemann, for Riemann, so you want to define the integral from a to b of f of x dx, and basically you decide to define gamma st is simply going to be f of s t minus s, and then the general Riemann sums, if you have delta a equals T0 less than or equal T1 less than or equal T2, etc. less than T2n equals B, then we would approximate integral from a to b of f of x dx is simply going to be, if you make the computation, this is just going to be sum from 0 to n minus 1 gamma tm plus 1 minus gamma, I'm sorry, I have to take into account, I'm doing here the most general Riemann sum, so I have, yeah, okay. This is gamma m t to m t to m plus 1 minus gamma t to m plus 1 to m plus 2, if I'm correct. I'm sorry. To m plus 2 to m plus 1. But if you do this, you will see that this is exactly what you expect, that this is just f of x t to m t to m plus 1. Am I correct? Just to be sure, because t2m plus 2 minus t2m. So this is the general approximation. So you imagine that you have the interval AB, you have the subdivision point T2, T4, blah blah blah, and then you have points where you evaluate f, and this is T1, T3. So did I write?
First of all, I mean, with the convention you wrote that gamma st as f of s, then obviously the t2m plus 1 should be in the first position.
Yes, and so let me yeah, okay, so t2m plus 1, it's correct, of course, as usual, I mean 2m plus 2 minus gamma 2m plus,
Maybe you want 2m plus 1 to
I guess you're right, then
you are going
2m
backwards,
plus 1
going
gamma
backwards,
2m.
so that's why you have
Yeah, exactly. Of course, I mean, when you're stupid like me, you better look at. I better look at my notes. Anyway, so this is the approximation you're going to make. And in the same vein, if you think about what we did when we did the Euler scheme for differential equations, we decided to have an approximation for what we called SPT of d of yu d xu, and maybe the notation xu would be better, but okay, so we decided that it was a good idea to approximate this as v of ys xt minus xs plus v of ys v prime of ys st. So this is essentially our gamma st. And so this was for differential equations. But if you think about it in an analogous way, imagine that you wanted to compute s to t, let's say, just trying to avoid writing something stupid on the. Imagine that you would do something like f of xu dxu. You would, in the same spirit, to go to the second order, you would just say that this is f of xs xt minus xs plus f prime of xs x ST, and this would be our gamma. Okay, so depending on the kind of integral you want to compute, you will use a different type of gammas. But you see, as I told you, this is something you don't know very much what it means, but this is very explicit, and then you can ask whether or not you get a convergent procedure if you refine the mesh. Okay. So and we think that, for instance, for the rough case, f of x dx from A to B exists if Riemann sums associated. So this is the rough integral. The corresponding ST have a limit. That's small mesh. Okay, so this was the motivation part. So this is to motivate that, in fact, it might be a good idea to just study more abstractly. Just don't be in an explicit situation, for instance, for a half part, but just study what happens to Riemann sums when you have a generic gamma ST. Okay. So now we go to what I call generalized Riemann sums. And as I told you, the data will be abstractly that I have some gamma that goes from AB squared to well, in fact, let's imagine that it's a real, but taking it with values in a vector space will be the same thing. And you imagine that A equals T0 less than or equal T1 blah 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 less than or T2n. B is a tagged subdivision. Well, then you define something that we call a gamma Riemann sum as delta of gamma A and B. By definition, I'm just copying what I did for the Riemann integral. This is just going to be sum from m equals 0 to n minus 1 gamma. I just copy it. So if I copied correctly what Jeremy told me, it should be correct. So this is my definition. And this is also a definition. Gamma is integrable so these are called gamma Riemann sums. The gamma is integrable with gamma Riemann sums have a small mesh limit. Okay.
Michel,
Yes.
do you suppose somewhere that alpha is between 1/2 and 1/3, or
There is nothing here. Oh, I mean, so here,
the second order of oscillation, you're taking the trapeze exhibition?
yes, essentially, yes. So indeed, I don't expect this to work very well if alpha is too small, and I expect this to be just improve the convergence, but not create convergence if alpha is too large and the right. But you know, this is just a motivation. So the integral exists if the corresponding sums have a limit. But that's fine.
Because if alpha is very small,
Yes.
could you go to the order of Simpson and so on?
Yes.
And,
It's not exactly Simpson, but yeah.
Parabolic or what?
Yes. Yeah, I would go further to the in the I would take the second derivative and this another guy here to play the well. So that's also something I will probably not have much time to talk about, but you can look at higher order abstract and define higher order objects. And indeed, the nice point with what we are going to do with gamma is that the same thing applies to all these guys. So you don't have to do a separate argument. There are some general results that will apply just blindly to all these guys. Okay, so gamma is integrable, and then the integral we denote by A to B of delta gamma, and sometimes I add the variable, but here it's even, well, you can add the variable if you want to. It might be useful in certain circumstances, but you don't even have to put the variable there. Okay, anyway. One thing that is useful is to look at advanced and retarded sums. They turn out to be useful. So you imagine now that delta is a subdivision. A equals to T0 blah 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 less than Tn equals B is a subdivision, not tagged, this one. And then I would also define the analogs. So this would be S retarded delta of gamma AB, and this would be nothing but sum from m equals 0 to n minus 1 gamma T m Tm plus 1. And you would also have the advanced one. Is B, and this would be sum of m equals 0 minus 1. I'm sorry, this, of course, as usual, I'm doing the advanced one would be gamma Tm plus 1 Tm plus 1 minus gamma Tm plus 1 Tm. And so I let you check that these are special associated to a particular class of tagged subdivision.
Can you discuss the difference between tagged and non-tagged?
Yes, tagged is when you put intermediate points to evaluate f, and non-tagged is you see for tagged you have two endpoints,
Okay.
and for non-tagged you have endpoints, and that's and they it's convenient to say that they are strictly ordered, and for tagged subdivisions, the T even are strictly ordered, and then you put the in. So these are called the subdivision points, and these are called the interpolation points, if you want. And so tagged subdivision is a subdivision, and then you add interpolation points in all the intervals. Is that clear?
Yes, and gamma TN10 is not necessarily 0.
Okay. That's just before the break. Let me. There is no special reason to say. Okay. So this is a good remark that I wanted to do anyway. So let's do it now. And once you have this, you could, for instance, if you look at things a la Ito somehow, you could be content that only the retarded sums have a limit, or only the advanced ones, or whatever. I mean, you could also define some kind of. You could add a symbol here like retarded or advanced or whatever, just to say that we are just considering these guys. So the remark is the following, that if gamma st is equal to some kind of to ft, then s delta gamma ab is identically 0 for any division. Okay, so if this is just okay, this is just really well. This is just trivial to check. You see, for instance, here, let's do it here. You see, if yes, if this one doesn't depend on the second argument, you just say this is just 0. Okay, and then by linearity, gamma st and gamma st reduced, which by definition is gamma st minus gamma ss, give rise to the same gamma Riemann sums. Yes.
Gamma st is just a function of f.
Yes, it's just a function of t.
Then you have a telescopic sum.
No, it's not that it's telescopic. It's just that because these arguments are the same, this doesn't depend on that. So this is just 0. You don't have in a telescopic sum. Usually, you have to push things one step to have the. Well, no, this is just every term is 0. Oh, I'm sorry. Sorry.
But then if you
It would
the
be telescopic
sum, and then
it would depend only on the extremities.
it depends only on the extremity.
Yes. No, no, thank you very much for that. And this is exactly what I implemented. Well, anyway. So,
Okay.
And it's okay. So the point. So this means that most of the time it's essentially harmless everywhere to decide that you look only at things here that vanish on the diagonal. But we'll see a situation where it's somehow more natural to keep the little piece on the diagonal as well. So
can you make it antisymmetric automatically or not?
well, no, you cannot make it as far as I understand, you cannot make it anti-symmetric the way you like. No, I don't think so. in the end, we expect that the integral will be somehow anti-symmetric, but and that's what is going to happen, but it's not needed. And so if your question is okay, I have to think about it. Then anyway, it's time for the break. So we'll.
Yeah.
10 minutes break.
Yes, okay, 10 minutes break. Okay.
I have to think about your question, Kiran.
Audio, Bing.
Okay, so we had this little point here. There is one point. Okay. I will make now. I start. Well, I can restart, Ricardo. Huh?
Yes, yes.
So that's something I wanted to say anyway, but Jeremy, I mentioned it right now because Jeremy made the observation during the break. He said the following: the existence of the integral depends only on the local behavior of gamma along the diagonal and obviously to express it correctly, if gamma st equals 0 or t minus s less than or equal to delta, then s delta gamma will be equals 0 as soon as the mesh is small enough. And then by linearity, if two gammas coincide close to the diagonal, then they are both integrable and have the same integral, or they are both non-integral. Okay, so this is the simple thing. So these are the simple things. Okay, so you see, this was, I can show you. This was really the one I was going to show just right now. So then these are just so this is what I call the subinterval property. Is that if you have ST included in AB and integral AB delta gamma exists, well, of course, if gamma is defined on the square, it's also defined on the subsquare ST, then in fact integral ST delta gamma exists as well. And then something very important, and which is, as I made the observation, just to start with, in fact, this is something one of the occasions to realize it is by looking at this abstract formalism. When you see, you approximate your integral by a sum of things. And then wouldn't it be extremely surprising if in the end you wouldn't satisfy Schall's relation? Because Schall's relation is exactly saying that the limit is going to have the same property, that you can get the full thing by summing some smaller things. So anyway, so Schall's relation holds. Integral S to U delta gamma is equal to integral S to T delta gamma integral t to u delta gamma. And this holds, to start with, as usual, this is true for s less than t less than u. But of course, once you have it, you can also decide that you define the integral when the bounds are not in the right order. You define it to be the opposite, and then this is valid, whatever st and u are. Okay, so this is.
So the definition of Riemann integrability really requires that the limit exists for type subunity
Yes.
function,
Yes.
and not just for the retarded or advanced.
No.
So there could be functions which are which you could define an integral in the advanced or retarded sense,
Yes.
and for which the generalized
Yes. Do I have an example?
so I don't know if I want to do.
No,
Because later I was wondering, you require exactly the same thing for you.
yes, exactly. Yes. And for instance, in the general case, for instance, that's very easy. You see, if you look only at advanced or retarded sums, you see these ones only look backwards, these ones only look forward. So you could do whatever you want on one side and something on the other side, so there is no guarantee at all. So in this generalized context, at least, this gives rise to different notions of integrals. Okay. For Riemann, I have to think. What next? So we have shell. What else? Okay, so there is one proviso here, however. If you look at the Riemann integral, if you're integrable on two intervals that share the common endpoint, then you're integrable on the union. This is not true in general. In this case, this is not true that if you have integral from a to b and from b to c, then you also have integral from a to c. If the tree exists, if the
for relation, you should add the
existence of
no, it holds. No, that's fine. It's just that if
it does not allow to define the left-hand side. It doesn't.
But if you only have those two guys, you're not sure that this one is going to exist. Yes. But if this one exists, then it's satisfied. And in fact, you can look for an example that's easy, or I can give you one. There is one property that is well, I don't want to mention it because it's going to take a bit too much time. Maybe I'll mention it sometimes when I need it. Okay, so no, I call it locality. Let's say it because, and it's the following fact that in fact so very often I will imagine that I'm in the reduced case, so I will not I will put to zero the diagonal. Anyway, if integral delta gamma AB exists, then we know that when the mesh is sufficiently small, I can approximate the integral by Riemann sums. But then you can do even a bit better. Then for sufficient, when the mesh of delta, which is a subdivision, is small, it's even better than that. In fact, then the sum m equals 0 to n minus 1 of gamma em plus 1 minus integral em plus 1 is less than epsilon, and you can do it in the reverse order. Gamma t m plus 1 m plus integral m plus 1 is small. So you see, if I move the absolute value sign outside, this is just the definition of integrability, but it's not too difficult to see that in fact you can put the absolute value inside, and it's useful because it's and it's essentially you can view it as a version of locality. It would be somehow shocking that you could have systematic compensations from one piece of the sum to the rest to make it conspire to give the right to the right integral, even if you would do something wild in small pieces. It would changing gamma. Well, anyway. And of course, it's easy to see that if you have those things, then this guarantees integrability, because it's some kind of absolute integrability or whatever. But and there is one last thing which is important and essentially obvious, but let me state it. So the detailed proofs of these properties, this one is a bit nasty if you want to do the details, but one thing that is important is that you can reparameterize so imagine that you have phi that goes from interval CD to interval AB, and it's arbitrary to start with, and you define the pullback. So I like it. I mean, employing some words in differential geometry. This is it. So phi star gamma UV. Do I do it? Is big surprise gamma phi of U phi of V. So this is the pullback, and then if phi is continuous, and integral AB delta gamma exists, then integral delta star gamma from C to D exists, and equals this one. Do I do it in the right order? Yes. And this is, well, this is very simple to check. Let me just say, it's just that if you have a continuous function and you look at what it does to subdivisions, when the mesh is small on one side, this is uniform continuity on the compact interval, whatever. If the mesh is small on one side, the phi is continuous and increasing. So it's a homeomorphism if you want. Then phi is going to map subdivisions to subdivisions and subdivisions with small mesh to subdivisions with small mesh. So that's uniform continuity. Anyway, so this is an important property. Okay, so now so this I hope is going to be some fun, and you can. This is what I'm going to say now is very preliminary in the way I think about it, but maybe you will help me at some point. And it's I call it an attempt at an analogy. So so this is a section. This is in my notes. This is section 3, but anyway. And so to simplify notation, just look at retarded sums. So we imagine that we define integrability only in terms of retarded sums and whatever. But, well, Charles' relation is preserved, and then many nice things are preserved. And so then and then gamma, I see it just as a map from AB squared less than or equal to R, and AB squared less than or equal. I define it by definition. It's just ST in AB S less than or equal to T. Okay. And I don't know exactly. I choose a fracture font to denote this in my notes, and I of course unable to. I'm not even able to say which letter it is, but I guess it's a Gothic G. It's the vector space of all such gammas. Okay. And it's a vector space, but you can also multiply. So it's an algebra. Okay, it's not so important. So we have gamma prime st is gamma st, gamma prime st. So it's you can also multiply if you want. Anyway, so and I would like to explain why I'm happy to see this space here as a toy version of a space of field theories. It's really a toy. I mean, it's really a toy. So a toy. Let's get off. And don't be afraid. I mean, it's so trivial that there are no anomalous dimensions. Well, you will see. Okay. So what do? I imagine so. Take U belonging to AB and define something that I call RU. RU gamma ST is going to be the following. It's going to be gamma ST if P is less than U or S is larger than U. And it's going to be gamma SU plus gamma UT if U belongs to the interval ST. Okay. So you see this somehow, for instance, this is a way to go from the trivial sum, the Riemann sum associated to the interval ST to the one associated to the one with the subdivision point U added. It's a way to insert a subdivision point. Maybe I should assume, let me assume that gamma equals 0 on the diagonal. Just because if not here, I might have some ambiguities, I guess. If I don't put 0 on the diagonal. And then it's easy to see I use commute. Okay. Ri is equal to Rb is equal to the identity. That's easy. And if I do it twice, Ru squared is equal to Ri within our projections. So I can compose them, and any composition RUs can be seen as taking gamma Riemann frame. Retarded associated with subdivision. So, well, because it doesn't make sense to take U, well, it's useless to take U several times. So you can if you do an arbitrary composition of these guys, you can assume that they are all distinct. Then you reorder them, and then what you end up with is just a retarded gamma Riemann sum. Okay. And also, this is so we have these transformations, and now if you look for fixed points, RU gamma equals gamma whatever U in AB. This is just equivalent. You see, this is just equivalent to say that nothing happens when you take when you make subdivisions. This means that obviously you're going to be convergent. The integral is going to exist, satisfy Schall's relation, so no surprise. There is a gamma hat such that gamma ST is gamma HT minus gamma HS. Okay, so it's easy. So if you think RU as local renormalization transformations, mesh delta as the cutoff of IPhT-0 So you use this, then you see, you start from gamma, you have renormalization transformations that move you around in your space sigma, and then you look if you reach a fixed point. Okay, so this is slightly unusual. I mean, but okay, we could be less demanding, in fact, and look only for, well, it would have some drawbacks, but we could, for instance, decide that at every step, we cut the interval AB in 2, and then in 4, and then in 8, and all that, and go on. You had a question?
Yes. Is this step obvious, or I mean, because if you do a finite sum, you have a finite RUs.
Yes.
And so figure. I mean, you could be a fixed point just for these U's, and depending how you choose your TM.
No, I mean, when I say it goes to fixed point under renormalization transform, I'm sorry. So delta as the inverse. First of all, I should say that the inverse cutoff. Maybe I should say it's a cutoff in real space. And when I say it goes to a fixed point under renormalization group transformations, when the cutoff goes to infinity. So which means the mesh goes to 0. So this is really the same definition. It's a triviality. It's there. Really, what I want to do is really get those TMs very. I only ask that you go to a limit when those TMs are very close to each other. This is really the same. I'm just paraphrasing the initial definition. So this is a bit different from the standard formulation of the renormalization group, because usually we really want to cut the scale by half at every step or double it. I don't know, it depends if you're in momentum or real space, but you do something, you cut by half or by 3 or whatever. But and here we do it step by step by adding one point at a time, and also we don't ask that we do it in a regular way. All we ask is that at some point we want the cutoff to go to infinity. So the mesh to go to 0. So yes. Yes. And then this gamma is going to satisfy Schall's relation. It is going to be the integral. I mean, it's just yeah. It's just a way to paraphrase all the thing. Nothing. Is that clear? You're welcome. Okay. So the only thing that is well, okay. So we are looking at local transformations. So we can decide that we are going to, for a while, that we are going to focus much more on one part of the interval than on the other. Look at that part with really des jumelles. Not twins. Huh?
Magnifying
glasses. Thank you. So you can really use magnifying glasses on one part of the interval before looking at it on the others. But in the end, nevertheless, you want the cutoff to go to infinity. So, but you do it in a local way somehow. Okay. So I will show you that in fact there is an equivalent. Okay, this is very general, gamma is arbitrary, whatever, but there is an equivalent of exponents also for that, though the exponents are trivial. What is interesting is that somehow, as far as I understand, it's easy to talk about fixed points, but then the naive way, you see everything is linear here, and really so the set of fixed points is a vector space and whatever. So the structure is very simple if you compare it to a space of field theories. However, as far as I understand, there is no way to analyze what is going on by using diagonalization. You cannot say, okay, now let's look, instead of looking at fixed points, let's look at those that just are multiplied by 2 when they make a renormalization group transformation, for instance, or well, whatever, or something is added, or I don't know exactly. Well, it doesn't work, and even looking for Jordan blocks, finite Jordan blocks doesn't work. So it's you see, the point is that when I look at the definition, where is it? I already erased what I wanted to keep. But anyway, so the point is that when you do a renormalization group transformation, you keep gamma intact on a large, on two. You have this big square here, which is AB, and then you imagine that here is U, I'm sorry, this is it's the square, and in fact you are going to leave gamma intact on a large piece, which is that one. This inside here, and I decided that I just wanted to keep under the diagonal. It's not really important, but there is a large piece that you don't move, so it's hard then to multiply. Well, anyway. So, well, the way you analyze it is slightly unusual as far as I understand. But let's see a little bit more precisely what we can do concretely to find examples where gamma leads to an integral. So this is really what deserves the name Ewing lemma, and we will see that it also leads to the existence of some critical exponents. Oh, okay. So, well, yeah, okay. Let me just before closing that, let me show you that there is some kind of robustness, like some primitive version of universality. So imagine that gamma is integrable. Or goes to a fixed point. And that gamma prime, let's just call it gamma tilde, is arbitrary but bounded. Okay, so it doesn't take arbitrarily large values. Then gamma tilde gamma is integrable if and only if gamma tilde delta gamma is integrable. And the integral is the same. So if you want, it's enough to know the ultraviolet behavior of gamma to decide whether or not this guy is going to be integrable.
The meaning of gamma tilde delta gamma.
Oh, I'm sorry. I'm sorry. Okay, integral delta gamma. Maybe. Yes. So this is. So I can use the ultraviolet quote unquote limit of gamma instead of gamma itself to decide whether or not this guy here is integral. And this is an immediate consequence of the integrability condition I gave here. So there are some well, and then some other things can be said, but there are a number of things that are quite analogous to the usual things we say when we talk about renormalization group transformations. So I will leave this. It's really primitive, but okay, I think there's some fun in it, and I will go now to something that really deserves the name. This is really called the Ewing lemma. And it's the following. Alpha belong to, yeah. Let's see, let's open it this way. And we say gamma, as usual, this goes from triangular if you have a certain condition, gamma S minus gamma ST minus gamma U plus, sorry, I don't want Jeremy to correct me in 1 second. I better look at my notes. TT less than K, something that I call STU. I want to call it gamma, this one. And this notation here, STU, this is the definition, this is max of S minus T, S minus U, T minus U. This is just the length of the smallest interval that contains the 3 points. Okay, so I say that it's triangular if it satisfies this condition. Okay. And then we have this important result, which is, I'm sorry, this is, we had a former colleague here who had his account on the machine was the directory was just, you know, the A and then subrepertory A and subdirectory A and subdirectory A, and he would move along that line. So I'm exactly doing the thing with the string lemma. This is the title of the chapter, then of the section, and then now it's the lemma itself. Then I will stop there. And the following, so if gamma is triangular of exponent gamma strictly larger than 1, then gamma is integrable. And the integral has, well, the property we established in general are the same. And there is something important which goes with it. The name, maybe it's good knowing because this is a standard. This is called the Euler inequality. But in fact, integral from A to B is delta gamma minus gamma AB minus gamma AA. I could forget about that one. This is always this is going to be less than 1 divided by 1 minus 2 minus 1 minus gamma K, this K here. B minus A. Gamma. So the error term you're going to make in your if you as we said, the whole point of this story was to approximate the integral by something some value for some useful thing, and indeed this inequality tells us that if we do so, the error we do is smaller than this. And for instance, this means that in this case in particular, that integral A to B delta gamma minus S delta of gamma AB, it's easy to see, this is going to be less than 1 over 1 to 1 minus gamma K B minus A, a mesh of delta to the power gamma minus 1. This you just do it by you just apply this inequality to subintervals and sum and blah blah. So this is easy. And so as I told you, this is one example. Of course, it's trivial because it's built in somehow. you see you have imposed this condition, and this is telling you the speed of convergence of this towards that. And so gamma minus 1 is an analog of the critical exponent. And again, the fact that we are looking at we just don't look at the dyadic subdivisions of the interval AB where we cut everything all the time in two and blah blah blah. We can do things locally. We can have magnifying glasses that look a bit more in one corner than in another and all that. These are not exact critical exponents. This is an upper bound. Lower bound, maybe I should say. Yes. Yes, it's one of the conditions. Of course, you see, with this generality, you can imagine delta gammas that have no regularity at all that work, gammas that have no regularity at all that work, for instance, because if gamma is a fixed point, it's the difference of two arbitrary functions which can be non-measurable, whatever, totally arbitrary, is going to be a fixed point, and then it means that it has an integral. So it's really it's a convenient, it's a useful condition, but it's not a it's probably not optimal. I mean, it's a useful and rather general one. There is no. Okay. Okay, so I will just give an immediate application to this little result. The proof is not very difficult, but it takes a number of steps and you have to organize yourself reasonably well. It will be in the notes, and if I have time at the end of the session, I will give you an outline of proof. The outline can be done quite shortly, but I would like to illustrate this on one relevant example, which is called the Young integral. So it will be a separate chapter in my notes, but let's do it today just to illustrate that this is useful somehow. So this is the Young integral. I will come back to it later, but let's do it partly today. So imagine that x, y are two functions from a, b to r. You could do something a bit more general for the one anyway. So then take something and the aim, define integral from a to b of ys dxs via analogues of Riemann sums. Yes. Yes. Well, it's Well, so the point is the following. This is all motivated by this idea of solving these controlled differential equations. And if you think about it in that way, it's much more natural to look at Riemann sums than to some kind of analog of measure theory. And so, for instance, okay, so that's a good point. Here, the conditions I'm going to place on X, for instance, is such that there is no way to, so maybe that's a good answer as well. We are going to allow X's that are irregular enough that dx is definitely not a measure in the sense of Lebesgue. So maybe that's the short answer. It's not so. Yeah. So it's so which means that X doesn't have to have finite variation, in fact, to say things differently. So this is these integrals are outside the scope of standard Lebesgue integration theory and measure theory. It's different. And but we had this discussion a little bit during the break. There are many areas where the right way to construct analogs of integrals is not via measure theory. Of course, there are many areas where measure theory is unavoidable and very nice and whatever. But there are also many areas in which the way to define integrals is not via measure theory. For instance, yeah. As far as I know, no. But my understanding of half path is limited, and very soon you will know as much about them as I do myself. So I don't think so, but I cannot be sure. And so another way to state it is that really what we want to do one special case of this would be to just to give a meaning to f of xs dxs from A to B. And if you think about it à la Lebesgue, you would like to deal with very irregular f's. Well, measurable, but which can have many discontinuities and all that. And the way we are going to look at things is this is going to be wild, and f is going to be rather reasonable. I mean, most of the time it will be Lipschitz or something. Okay. So I think the two ways of looking at integrals are a bit orthogonal. Of course, they have in common Schall's relation when it is defined and things like that. But it's rather different, I would say. Okay, we want to define this via analogs of Riemann sums. Okay, and so now I claim that this is to consider gamma st to be ys xt, or equivalently ys xt minus xs. You see, this is just a way to reduce. I'm subtracting something that depends only on s, and this is the one which we are familiar with. We would like to approximate the integral with that. Yeah. Ys dxs will be somehow equal to ya xc minus xa if p minus a is 4. And then there is Young's theorem. Okay, so again, it's easy to see that in fact, if you redo the theorem, well, you have this reparametrization invariance. You see, one of the drawbacks of this condition here is that it violates reparametrization invariance. It's not reparametrization invariant, this condition in the triangular property. And you are going to do the same here, but in general, I don't know how to do. For this case, there is a way to define these integrals more generally, not on Hölder spaces, but on finite variation spaces of a certain exponent. But anyway, so we shall stick to this elementary triangular lemma, and we have the following. X is alpha Hölder, and Y beta Hölder. With alpha plus beta strictly larger than 1, then gamma Riemann sums converge ys dxs defines exists as a limit gamma Riemann sums. Yes. Yes. Well, we say that it's the triangularity makes sense. Whatever gamma is, it could even be negative if I wanted. But the point is that then, if you want the integral to exist, you have to impose that gamma is larger than 1. Triangularity makes sense for. Yes, and in fact, this is one of the rare cases of when I can give a proof. When I can give a proof based on the Swing lemma. The proof is the following: is that in fact gamma is alpha plus beta triangular. So let me compute it using these guys. It's easy to see that gamma SQ minus gamma ST minus gamma TU plus gamma TT. If I made no mistake, I hope so, this is going to be simply YT minus YS XU minus XT. If you think about it, there is a very nice rearrangement, and this is the simplest version of Young-Baxter that I can think of. It's not the same Young. No, it's not the same Young, and it's Young. That's correct. Young-Baxter for dummies. Well, anyway, so this holds. This is simple computation, and this then you see that then the absolute value of this is less than a certain constant relating to y times t minus s to the beta, a certain constant for x u minus t to the alpha. And this is less than kx, ky, what I called s u to the alpha 3. So this is essentially a one-line proof of the existence of the Young integral based on the Swing lemma. So we have to know the Swing lemma before. But you see, it does the job. And exercise, in fact, give a simple condition. Yes? There's a question?
No.
Give a simple condition on f such that the half integral AB f of x d x exists if gamma st is equal to f of x s x t minus xs plus f prime of xs st. So you see, you have some regularity conditions here, some regularity conditions there. You do the little computation of this thing for this guy. You look at what it gives. You use chance relations. They play a role, and then it should tell you that there is a very simple condition on f for the Swing lemma to apply, and so you have again a one-liner proof of the existence of half integrals, which is, I mean, of course, much less. Well, it's definitely much less painful to realize that these two theorems fall under the same general pattern than to do the computations explicitly in each case. So you will see that there is a very simple condition on f. Okay, so let me just say one thing, because I have to use my time as fully as I can, because if not, it will be paid at the end of the lectures. So let me just mention the following, because it's related to something we discussed at length before, and it plays a very important role in many areas of analysis. There is a little lemma, which is easy, which is the following. Integral from a to b xs dxs exists in the Young sense. Gamma st is equal to xs xt minus xs and Riemann. If and only if x has vanishing variation limit mesh delta equal to 0 sum of x tm plus 1 minus x tm squared is equal to 0. So you see, this gives somehow an intuitive explanation for the things we found during the first lecture when we analyzed differential equations. Because recall what we said morally, dx dy equals v of y dx can be solved via the first order Euler scheme if x has 0 variation. One L, two L's, two morally.
Two.
Morally, there are two L's in morally yesterday. Thank you. So it's easy to see, well, and then we add the corollary, then integral A of B to B f of x s bxs exists as soon as is Lipschitz. So this is an easy exercise, and this gives the explanation why you can expect that this is going to work. It means that in fact the integrals you write down make sense when you solve this with the first order Euler scheme. And in particular, there is a natural meaning to the you see. Once this, I'm sorry, this exists, and the value, I'm sorry, maybe I should add, the value is, well, it's not a surprise. Okay, so you can convince yourself that indeed when you are going to solve iteratively this, basically this result is going to apply little by little to give you the fact that you will succeed in solving the control differential equation. The deep reason is really this. Okay. I should stop here today. Thank you.
So we can employ the last 2 minutes with questions.
There are 2 minutes left.
If I trust.
Because that was the time when we resumed. Oh, I should have said. I should. Start a new chapter.
Okay. Are there more questions here or in the virtual room? Virtual students?
You said that you would give a sketch.
Well, but even the sketch would probably take a bit too much time.
More than
Well, in 1 minute, I can say, okay, so first of all, prove convergence if you just look at dyadic subdivisions of AB, essentially. There is a little trick there, but you do it, and then it's easy. You show that there is some kind of, you show the convergence of a series by showing that it's absolutely, you have a sequence, and you show that it's in fact absolutely convergent. Okay, so that's it. And then once you've got this one and shown that the result satisfies the Schall's inequality, Schall's relation, then it's easy to show that the retarded, all the retarded sums have a limit, and then you do all the sums. So it's in 3 steps. Retarded dyadic sums, retarded sums. And for the dyadic sums, you have to play a little trick if you want the Schall relation to come out easily. That's 1 minute. But the strategy is in the notes, will be in the notes, and then the proof will be in the notes.
More questions?
And I'm afraid that at the end of the 4
Okay.
lectures, I will have done only half what I wanted to do. Which is nevertheless all I know. I mean.
Okay.